Dear students, this is the recorded class for Aldehydes and Ketones, Module 2, and we will be discussing about the following topics, that is reduction of aldehydes and ketones using metal hydrides with mechanism, then MPV reduction, Clemenson's and Wolff-Kishner reduction, then oxidation of aldehydes and ketones using potassium permanganate, Tollens reagent, Felling solution, Bromine water, open air oxidation, and Baeyer-Villiers oxidation. First of all, we will learn what an oxidation ladder is. Since we are dealing with the oxidation reduction reactions, we have to know about oxidation ladders. So these type of concepts are used to illustrate the sequence of carbonyl compounds which can be interconverted through oxidations or reductions. So you can see an oxidation ladder here. So in this, at the bottommost part, there is an alkane which is oxidized to a primary or a secondary alcohol, which is again oxidized to an aldehyde or a ketone. And the higher members of the oxidation ladder is carboxylic acid, ester, or acid halides. So you can see that as you climb up the ladder, the oxidation state of the carbon is increasing, and as you go down the ladder, the oxidation state of carbon is seen decreasing. This is an oxidation ladder showing the oxidation of aldehydes to carboxylic acid, and the higher members here is the carboxylic acid. And this carboxylic acid, when it is reduced, you get an aldehyde, and when this aldehyde is again reduced, you get a primary alcohol, then an alkane. So examples for the reductants are sodium borohydride and lithium aluminum hydride. And examples for oxidants used for these processes are PCC and H2CrO4. So the topmost part is the compounds that are most oxidized, and the bottommost part of the ladder is the compounds that are the least oxidized. This is another oxidation ladder. It shows the oxidation and reduction of the ketones. So the oxidation of ketones will give ester, and the reduction of ketones will give secondary alcohols and subsequently alkanes. So there are also horizontal ladders which does not signify any oxidation or reduction reactions. So this is also a useful concept for organizing reactions that don't involve climbing or descending the oxidation ladder. For example, alkenes can be converted into either a primary or a secondary alcohol depending on the choice of the reagent, and either of these can be converted back to alkenes. So these are actually not oxidation or reduction reactions. Only the change is that the alkene functional group is being changed to the OH group. So only the functional groups are interconverted. Similarly, alkynes can be converted to either an aldehyde or a ketone, and depending on the choice of the reagents. So neither of these transformations are considered as oxidation or reduction reactions. So let us understand what all reactions can be considered as reduction reactions and what all reactions can be considered as oxidation reactions. So a reduction reaction, if an addition of a hydrogen to an organic compound occurs, it can be considered as a reduction reaction. And if an addition of an electron occurs, it is also a reduction reaction. Then removal of the oxygen is also a reduction reaction. Similarly, just the opposite. In the case of oxidation reactions, the removal of hydrogen, removal of an electron, and addition of an oxygen can be considered as oxidation reactions. Let us see the reduction reactions of aldehydes and ketones first. In this structure, you can see an aldehyde is being reduced to a primary alcohol. So this is a hydrogenation reaction. that is a total of a hydrogen molecule H2 is added to an aldehyde. So this is a reduction reaction, and the reverse of this reaction is dehydrogenation. A dehydrogenation is an oxidation reaction. So how this hydrogen molecule is added to an aldehyde? It is added as two parts. First, a hydride transfer occurs. Since the CO bond is polar, the H minus will come and attack the carbonyl. So here a hydride ion transfer occurs in the first step, and subsequently the proton part of the H2 molecule attached to the O minus formed. So this process, that is the process of addition of a hydrogen molecule to an aldehyde group, is a reduction reaction. So hydrogenation and dehydrogenation reactions, these are called hydride transfer reactions, and because a hydride ion is transferred from the molecule being oxidized to the one being reduced. Let us now see the reduction reactions using metal hydrides. So there are two most important metal hydrides used for reduction reactions. The first one is the lithium aluminium hydride. Lithium aluminium hydride, that is LiAlH4. Here the Li plus is the positive part and the AlH4 minus is the negative part. It is also called as LaH, lithium aluminium hydride. And the second metal hydride which is commonly used is a sodium borohydride. Here sodium borohydride, the Na plus is the positive part and BH4 minus is the negative part. So in the case of a sodium borohydride, if we are using the sodium borohydride, it reduces only the CO group but not the C double bond C in the molecule. So sodium borohydride is a highly selective reagent. It selectively reduces the carbonyl group and it does not affect the C double bond C of the molecule. But lithium aluminium hydride is a much stronger reducing agent and it is very difficult to handle. So this is a stronger agent. This is because the AlH bond here is very weak. So it can easily dissociate and give the H minus, that is the hydride ions, to the molecule, to the substrate that has to be reduced. So the AlH bond is very weaker than the BH bond. Therefore, the lithium aluminium hydride is a stronger reducing agent than the sodium borohydride. But the sodium borohydride is a very selective reagent and it will only reduce the C double bond O in the molecule. Let us see a few examples here. A butanone is being reduced to 2-butanol using lithium aluminium hydride. Whereas when we use sodium borohydride also we get 2-butanol. So in the case of carbonyl compounds having only a C double bond O, the products are the same. If we are using lithium aluminium hydride or we are using sodium borohydride, we get the same product. Since the sodium borohydride is a mild reducing agent, we usually prefer the sodium borohydride for a reduction of aldehydes and ketones. Another advantage of using sodium borohydride is that it reduces the aldehydes and ketones rapidly, but it reduces the esters only very slowly. So this is an advantage of using sodium borohydride. So therefore the aldehydes and ketones of the carbonyl group can be reduced without the simultaneous reduction of the ester group in the same molecule, and this selectivity is not possible with lithium aluminium hydride. Let us see this compound. So this compound is having an aldehyde group as well as an ester group. So if you are using a sodium borohydride, this ester group is not reduced. Only the aldehyde group is reduced to the alcohol. So this is how a selectivity for this reaction can be obtained using sodium borohydride. Let us see the mechanism of reduction of So using sodium borohydride. The first step is the hydride ion transfer. So the metal hydride, that is the BH4 minus part, react with the carbonyl part, and it will transfer a hydride ion to the carbonyl's carbon. This is the first step. So the negative hydride ion is transferred to the positively charged carbon of the carbonyl group. So this gives an alkoxide ion like this. Here the oxygen is having the negative charge. Again, there are 3 more hydrogens present in the BH3. So the BH4 minus is converted to BH3. There are 3 more hydrogens present here. The second step is the protonation of this alkoxide. For that, the H plus ion from the medium come and attach to the O minus, and we get an alcohol as the resultant product. So each hydride ion can reduce one carbonyl group. Therefore, 1 mole of the sodium borohydride can reduce around 4 moles of aldehydes or ketones. Let us see the mechanism of reduction using lithium aluminium hydride. In lithium aluminium hydride also, the first step is the hydride ion transfer from the AlH4 minus group. So here the hydride ion H minus is transferred to the positively charged carbon, and we get a resultant alkoxide ion having an oxygen with a negative charge. Then an Li plus ion will accompany this negative charge, and the byproduct is AlH3, which is obtained from the AlH4 minus. And second step is, of course, the protonation of this alkoxide. So the water from the medium add a proton to the O minus, and we get the alcohol, and we will also get LiOH as a byproduct. These are the reactions shown in your text. The first reaction, an acetaldehyde is reduced using lithium aluminium hydride or sodium borohydride to a primary alcohol, and a ketone, that is an acetone, is also reduced to a secondary alcohol here using either LiAlH4 or NaBH4, and you can also reduce benzaldehyde to benzyl alcohol using either of these reagents. Another important application of this metal hydride reduction is the conversion of cinnamaldehyde to cinnamyl alcohol. So this is the structure of cinnamaldehyde. It is having a carbonyl group and a C double bond C attached to a phenyl ring. So if you are using sodium borohydride, it will only reduce the carbonyl part to the OH. Whereas if you are using a lithium aluminium hydride, it is a much more stronger reducing agent than the sodium borohydride. Therefore, it will reduce both the carbonyl part and the C double bond C. So here you get an alcohol here without any saturation. In order to prevent this reduction of this double bond, we can take one equivalent of LiAlH4. So we have to reduce the amount of LiAlH4 taken for this reaction, and in this case it will only reduce the aldehyde carbonyl group only, and it will not reduce the C double bond C. So this is because LiAlH4 is a very strong reducing agent than the sodium borohydride. And another thing is that LiAlH4 does not affect this isolated carbon-carbon double bond. So here this is the alpha carbon and this is the beta carbon. So here this double bond is not in conjugation with the carbonyl group, therefore this is isolated. So such type of double bonds will not be reduced by lithium aluminium hydride. Another method for reducing the carbonyl group is using metal catalyst, that is by the process of catalytic hydrogenation. So hydrogen gas with a catalyst is used for reducing the carbon-carbon double bond here. So this is not a very selective reaction. Here, in addition to the carbonyl group, the C double bond C is also reduced. So one of the widely used reactions in the industry is the catalytic hydrogenation using Raney nickel. And this is a finely divided nickel powder which is saturated with hydrogen gas. And instead of nickel, we also use platinum and rhodium metal catalyst also. So let us see these two reactions. If both a double bond and a carbonyl group is present in a structure, so in this case the double bond may be hydrogenated leaving the carbonyl group intact, or both may be hydrogenated. So if in the first reaction, this is a reaction of 3-pentenyl, and if you are using a nickel catalyst at 25 degrees Celsius for hydrogenating, it will only hydrogenate the C double bond C, whereas the aldehyde group will remain as such. So we get a product pentenyl. So if we use the same catalyst at a higher temperature and pressure, then more number of hydrogen molecules will come to action. So it will increase the activity of this molecule. So in this case, both the double bond C double bond C and the aldehydic carbonyl group is also reduced. So at higher temperatures, the activity of this reaction will be, the rate of this reaction will be very high. So we get 1 pentanol here. Let us see another example for catalytic hydrogenation using platinum catalyst. Here a cyclohexanone, that is a ketone, is hydrogenated using platinum catalyst, and we get cyclohexanol. The carbonyl group is reduced to the OH. This is a secondary alcohol. Now if we are taking an aldehyde, that is acetaldehyde, using the same catalyst and condition, we get ethanol, that is a primary alcohol. Biomolecular reduction. Biomolecular reduction is a method to reduce ketones. So ketones will be reduced in presence of magnesium. So we get a compound like this, a cyclic compound like this. Since magnesium is having a +2 oxidation state, it can form complex with these two oxygens of the two ketones. So we get a cyclic compound involving a magnesium ion. So in the next step, this compound is hydrolyzed, and this magnesium will be removed from here, and two OH groups will be substituted at these adjacent carbons. So this is the resulting structure. We get two OH groups attached to two adjacent carbons. This is called pinacol. This structure's name is pinacol. So you can obtain a pinacol from a ketone. So these are called bimolecular reactions because two molecules of ketones are involved in this reaction. So on a total, this is a reduction reaction. Next is reductive amination. So in this type of reactions, an aldehyde or a ketone, on treating with hydrogen and ammonia in the presence of nickel catalyst, gives the corresponding primary amines. So here, as a reaction involves a reduction as well as an amination, this reaction is called reductive amination. Here you can see a ketone, acetone, which is treated with ammonia and hydrogen in presence of nickel. So here the carbonyl oxygen will be removed and the NH2 group will be substituted at this position, and the carbon will also get a hydrogen. So this is a product isopropyl amine. There is two CH3 group, then a CH NH2 group. Similar reaction is also there with the aromatic ketones. Here also the C double bond O will be removed and CH NH2 group will be formed. So this type of reaction is called a reductive amination. Next is deoxygenation reactions, that is the removal of oxygen. This type of reactions are also considered as reduction reactions. So there are two important reactions to be learned in this section. First is the Clemenson's reduction. Clemenson's reduction, that is if the molecule is stable in hot acid, we can use Clemenson's reduction. And the second one is Wolff-Kishner reduction. And this type of reduction reactions is used if the molecule is stable in very strong base. Clemenson's reduction. In this, an aldehyde or ketones on reduction with zinc amalgam and concentrated HCl gives the corresponding hydrocarbons. So Clemenson's reduction is used for the reduction of an aldehyde or a ketone to its corresponding hydrocarbons, and we use zinc amalgam and HCl for this reaction. Since Clemenson's reduction is carried out in acidic conditions, it may be conveniently used for the reduction of carbonyl compounds which are sensitive to bases. Second type of reaction is the Wolff-Kishner reduction. So here, when an aldehyde or a ketone is treated with hydrazine and potassium hydroxide, hydrazine is NH2. So when an aldehyde or a ketone is treated with hydrazine and potassium hydroxide in a high boiling solvent like ethylene glycol, the carbonyl group is reduced to methylene group to form the corresponding hydrocarbon, and this reaction is called the Wolff-Kishner reaction. Wolff-Kishner reduction reaction. The first step, when this hydrazine is reacted with the aldehyde or the keto group, the C double bond is reduced. This oxygen and the two hydrogens from this hydrazine will condense to form the leave as a water molecule, and this C double bond N NH2 will be formed. This is the product here, C double bond N NH2, and this again in the presence of a base, that is C2H5O minus is a base and Na plus is accompanying cation here. So this compound in the presence of a base, this bond will be cleaved and a hydrogen will be added at this carbon. So here we get a CH3 here, and the nitrogen molecule will be another byproduct. So this aldehyde is reduced to the corresponding hydrocarbon here. So we can see another example, that is a ketone. A ketone also, when treated with a hydrazine, it will react forming a compound like this, that is a water molecule is lost, and this nitrogen and this carbon will be double bonded, that is its product. And this, when subsequently treated with a base, we get a corresponding hydrocarbon. So here there is 3 carbons, you can see CH3, CH3. So here 2 hydrogens will be added here, so we get a 3 carbon product, that is CH3, CH2, CH3, and the nitrogen as another byproduct. So this is the Wolff-Kishner reduction. So these 2 reactions are very important for your exams. Next is the MPV reduction, that is Mervin-Pondorf-Verley reduction. So this is a short form of MPV. So this is the reduction of aldehydes or ketones using aluminium isopropoxide. So here aluminium isopropoxide is used for reducing the aldehydes or ketones. So here aldehydes and ketones are reduced to alcohols by treating it with solution of aluminium isopropoxide in isopropanol as a solvent. So this type of reactions are reversible reaction. And the reverse of this reaction is the open air oxidation. So let us understand this reaction. Here you can see a carbonyl compound, and this is a ketone. This ketone is treated with aluminium isopropoxide in the excess of solvent, that is an alcohol here. So this ketone is reduced to alcohol, and the solvent alcohol is oxidized to a ketone. So this first reaction is the MPV reduction reaction. So as said earlier, The reverse of this reaction is the open air oxidation. Here you can see an alcohol. An alcohol is oxidized to a ketone here. Here we take another ketone as a solvent in excess, and we use the same catalyst, that is aluminum isopropoxide. So this alcohol is oxidized to a keto compound, and this excess of acetone solvent is reduced to a alcohol. So these two are reverse reactions, MPV reduction reaction and open air oxidation reduction. The advantage of this MPV reduction reaction lies in its high chemoselectivity, and it also uses very cheap and environmental friendly metal catalyst like this. Now let us see the oxidation reactions of aldehydes and ketones. Aldehydes are readily oxidized even with mild oxidizing agents like Tollens reagent, while ketones are oxidized only under drastic conditions. So let us first see the oxidation of aldehyde. So the common oxidizing agents like potassium permanganate, acidified potassium dichromate, etc. can oxidize these aldehydes to carboxylic acids. And the acid formed has the same number of carbon atoms as in the aldehydes. So aldehydes are oxidized much more readily when compared to ketones, and as a result the aldehydes can reduce even mild oxidizing reagents. So here you can see the acetaldehyde, and we use a reducing agent either KMnO4 or potassium dichromate, K2Cr2O7. In both the cases we get a carboxylic acid here, and there are same number of carbon atoms. So the CHO group is converted to COOH group. So mild oxidizing reagents like a Tollens reagent, Fehling solution, etc. can be used to distinguish between aldehydes and ketones, because these mild oxidizing agents will oxidize only aldehydes and it will not perform any reactions on ketones. Let us see such kind of reactions. First is a reaction with Tollens reagent. So Tollens reagent is ammoniacal silver nitrate solution. So it is prepared by the addition of ammonium hydroxide and silver nitrate, NH4OH and AgNO3. Aqueous ammonium hydroxide and silver nitrate is mixed, and we get a silver hydroxide as a precipitate initially, and this initially formed precipitate will again dissolve when this excess reagent is added. So this is the Tollens reagent. So when an aldehyde is treated with Tollens reagent, we get a carboxylic acid, and a silver mirror is formed as a result of the deposition of silver ions in the test tube. So this reaction is not given by ketones. A second reaction is the reaction with Fehling solution. So here Fehling solution is actually a mixture of Fehling solution A and Fehling solution B. So Fehling solution A is copper sulfate solution, and Fehling solution B is sodium hydroxide solution containing Rochelle salt, that is sodium potassium tartrate, in equal volumes. We take Fehling solution A and Fehling solution B in equal volumes. So when an aliphatic aldehyde is treated with this Fehling solution, it is oxidized to a carboxylate group, and this copper present in this Fehling solution is reduced to red precipitate, that is cuprous oxide. So the formation of this red precipitate indicates that the material given to us will be an aldehyde. So this reaction is also given only by aldehydes, and ketones will not give this reaction. Next is the solution with Benedict, reaction with Benedict solution, and this is also a third kind of test for aldehydes alone. So Benedict solution is a solution of copper sulfate, sodium citrate and sodium carbonate. Here, when an aliphatic aldehyde is heated with this Benedict solution, we get a reddish brown precipitate, that is a cuprous oxide, and this aldehyde group is oxidized to the carboxylate group, and ketones do not give this Benedict solution reaction, and ketones do not reduce Fehling solution, Benedict solution and tolerance reagents. So all these tests can be used to distinguish between aldehydes and ketones. Another common reaction is the oxidation with bromine water. So bromine water oxidizes aldehydes but not the ketones. So here aldehydes, the first carbon, there will be a carbonyl group, and this carbonyl group is converted to an acid, a carboxylate group, using bromine water test. So here you can see an aldose which is being converted to aldonic acid or glyconic acid. So another example is the conversion of glucose. Glucose is also having a CHO at the first carbon, and this is converted to a COOH group using bromine water. So glucose is converted to gluconic acid. So if you are taking a ketose here, for example D-fructose, this is a ketone. So here the first carbon is not having any aldehyde group, but only the second carbon, that is the C2, is having a carbonyl group. So this type of compounds, that is the ketones, will not give any reaction with bromine water. Then we discussed about the open-air oxidation, which is just the reverse of the Mervin-Pond-Oeverly reduction, MPV reduction. So here in the oxidation of this open-air oxidation process, it is the oxidation of an alcohol with aluminium isoperoxide in excess of acetone. So you get an alcohol being converted to a keto group here. So this is a oxidation step, and the other reaction, a parallel reaction, is that this acetone, which was the solvent, is reduced to the alcohol here. So the oxidation of primary and secondary alcohols with ketones in the presence of metal alkoxide, for example aluminium isoperoxide, to the corresponding aldehydes and ketones, is known as the open-air oxidation process. Let us see some of the advantages of this type of reactions. So here you see in this reaction in your text, and this is a secondary alcohol which is being oxidized to a ketone using the aluminium isoperoxide. So here the advantage is that it uses a relatively inexpensive and toxic reagents like this one. And the second advantage is that the reaction conditions are very mild and gentle, and also this type of reaction can be used to oxidize secondary alcohols, because secondary alcohols oxidation is much faster than the primary alcohols. Therefore we can attain a chemoselectivity for this type of reaction. By using this type of reactions, we can attain a chemoselectivity. The secondary alcohols will be oxidized much faster than the primary alcohols. Next reaction is the Baeyer-Willigers oxidation reaction. So Baeyer-Willigers oxidation reaction is also a very convenient method for the conversion of an aldehyde or a ketone to an ester. So here we take a peroxycarboxylic acid for this reaction. So in the peroxycarboxylic acid, we know that there are reactive oxygen. So these one of this oxygen will be inserted into the C bond here in the carbonyl compound. So here in this case acetophenone is converted to a phenyl acetate. Here the oxygen from this peroxycarboxylic acid is being inverted to this bond, that is C6H5C bond. Here you can see an extra oxygen present in this compound. This is phenyl acetate. This is an ester. So here a ketone is being converted to an ester here. So this is the Baeyer-Villiers oxidation. So in Baeyer-Villiers oxidation, we use a peroxycarboxylic acid for the conversion of an aldehyde or a ketone to an ester. And this conversion occurs by the insertion of an oxygen atom from this peroxycarboxylic acid. So it is also used for the conversion of cyclic esters, that is lactones. Here this is not a cyclic ester. Okay, so if this compound is in a cyclic shape, we call it as lactones. And we can see a few examples here. You can see a cyclic ester. This is a cycloketone. The second expression here. So this is a cycloketone. Cycloketone, when treated with the peroxy acid, an extra oxygen is inserted into this ring. So you get a lactone here. So the ring number increases. The number of atoms in the ring increases. So this is a lactone. So Baeyer-Villiers oxidation reactions are also used for the preparation of cyclic ketones or lactones like this. Let us see a few examples. First example is the oxidation of acetophenone to methyl benzoate ester. Here we use trifluroperacetic acid as the peroxy acid. In this case, the peracetic acids, 3 hydrogens is replaced by the 3 fluorine atom. So this peroxy acid is called trifluroperacetic acid. So this acid is used for the conversion of acetophenone to methyl benzoate. So this is an ester and this is a ketone. Again, another example, this is a cyclohexanone being converted to a caprolactone. Here also the oxygen is a part of the ring. So cyclohexanone was a 6-membered ring, and the 6-membered ring is converted to a 7-membered ring. This is a lactone. So let us see the applications of Baeyer-Villiers oxidation. So Baeyer-Villiers oxidation, it is used for the synthesis of lactones. So this lactone is a very industrially important compound because it will contribute significantly towards flavoring agents for the flavor of fruits and unfermented and fermented dietary products. And hence they are used for flavor and fragrance. This is the important application of Baeyer-Villiers oxidation reaction. And finally, we will learn about haloform reactions. So in this reaction, an aldehyde or a ketone containing a CH3CO group is warmed with a halogen. Here we can see an iodine here in the presence of an alkali. So this aldehyde or a ketone, it should have a CH3CO group. So CH3CHO group is having a CH3CHO molecule is having a CH3CO group. That is a terminal part. There is a CH3 group attached to a carbonyl group. So this type of compounds will only give the haloform reactions. So this type of compounds, when reacted with halogens, the 3 hydrogens will be replaced by 3 halogen atom. You can see the Ci3CHO. And this product, when again treated with the sodium hydroxide, CHI3 is formed. So this is the haloform. The name of this haloform is iodoform. So if in the case of a chlorine, we get a chloroform, that is CHCl3. Here we get a iodoform, and the byproduct is HCOONA. You can see another example, that is a ketone, acetone. In acetone also there is CH3CO part. So here the first 3 hydrogens of the first carbon will be replaced by the iodine, we get CI3COCH3, and this again reacts with sodium hydroxide in the medium, and you get the iodoform CHI3 and the sodium acetate as the byproduct. So haloform reactions are also used for the identification of compounds containing a CH3CO group, or the compounds which can produce this type of groups under any experimental conditions. So these are all the portions coming under the oxidation and reduction reactions of carbonyl compounds, that is aldehydes and ketones. So if you want, you can try writing the mechanism for this reaction, how a benzaldehyde is converted to benzoic acid. So that's all for this video. Thank you.